So today in artificial intelligence and soft computing we'll see a third type of uninformed search strategy. Okay, in a previous lectures we have seen what is a breadth first search, what is depth first search, and now we'll see a depth limited search strategy. So a depth limited search strategy is not a new type of searching strategy, but it is doing some modification, or it is having some modification or upgradation in a depth first search strategy. What happens whenever you are dealing along with the depth first search? If the depth of a tree will be high, means your problem will be a complex problem. Under that situation, it's as per a depth first search strategy, you are searching a particular goal node across one of the branch, and if a complexity of problem will be large, then you are going till the depth, or we can say a leaf node of that particular branch, and if we are not getting a particular goal node, then we are backtracking from that particular node and we are reaching to a particular point from which we have branched or we have explored. So this is a time consuming process if the problem will be a complex problem. Under that situation, it reduces the efficiency of a searching process. To avoid these all problems, the new searching strategy evolved, that is called as a depth limited search strategy. In a today's lecture, we'll see what is a depth limited search strategy. So we'll take one of the example. Okay, that is having we'll take one of the tree. Suppose we are having a node A, we are having a node B, we are having a node C, we are having a node D, and we are having a node E. Okay, suppose this is a particular tree out of which this is nothing but your initial state and this is nothing but your goal state. Okay, so this is level 1, this is level 2, this is level 3, and this is level 4. So as per depth first search strategy, if you are interested to explore, okay, this particular tree, and if you are interested to get a goal node, okay, so as per a depth first search strategy, as this is uninformed search strategy, so suppose we are checking this particular node A. If it is not a goal node, if A is not a goal node, then definitely we are interested to check whether it is having some successors. Okay, so if we are having a success, it is having a successor, then we are going to explore them and we are going to add them to a stack. So suppose I'll open this node first, C. Okay, so I'll take one stack, I'm opening this node C first, then I'm opening this node B. Okay, means I'm adding this C first into a stack and then I'm adding B into a stack. So my topmost element of my stack will be a B element. So if I'm opening this B next, means B is coming as the topmost element of my stack, then definitely I'm going to explore this node B. So I'm going to explore this B and I'm going to check whether B is a goal node. If B is not a goal node, then I'm going to check whether it is having successors. If it is having successors, I'm going to add them into a stack. Okay, and I'm going to close, definitely I'm going to close this particular B. So now D is my topmost element, so I'll cross check this D element. If this is not a goal node, then I'm going to check whether D is having successor. Yes, D is having successor, so I'll add that successor into my stack. So topmost element of my stack is nothing but a E. So this particular element I'll cross check across my goal node. If this is a goal node, then it's okay. If this is not a goal node, then I'm going to check whether it is having successors. If it is not having successors, then I have to again backtrack, okay, to my original node, and then I have to move to this particular node C. Okay, I'm backtracking from this to this, this to this, this to this, and then I'm moving to C, means the C will be visited last. Okay, so this is a worst situation. If now we are taking only a 4 level, so it is looking easy, but if we are trying for a maximum level. Suppose we are moving in a this particular branch, okay, so on, then this is becoming a time consuming process or hectic process. Okay, to avoid this, a depth limited search has been modified to devise a depth first search is modified to devise a depth limited search. Limited search. So what is this depth limited search? Okay, depth limited means we are putting a limit on a depth up to which we should search, or we should carry out a searching process. Suppose at this moment I am putting a depth limit alpha is equal to 1. Alpha is nothing but a depth limit, a particular symbol we are assigning for a limit. Okay, so alpha is equal to 1. So a tree logically available for searching process is up to this. I'll check, I'll open this particular node A, I'll put it into a stack. Now topmost element is nothing but A. I'll cross check it across a particular goal node. If it is matching, then it's okay, print succeed and stop there. If it is not matching, then we have to print a result, a tree searching trees over. Okay, my stack is empty and I have to terminate there. Okay, if I'm assigning up level 2, then I'll explore up to this particular level. Means tree logically available for carrying out a searching process is A, B and C. I'll explore this A, I'll check whether A is a goal node. If A is a goal node, print succeed and stop there. If A is not a goal node, then check whether it is having successors. Yes, it is having successors. So I'll open C, I'll open B. Now topmost element is a B, I'll cross check B. If not goal node, then I'll check its successors, but successors are not available because we are having a logical tree available that is up to a level 2. So I'll move to node C, I'll get a goal node and I'll terminate, okay, in this particular tree. Okay, so this is a depth limited search strategy, okay, which is putting a limit up to which we should carry out a searching process. Okay, in a depth first search we are going up to a depth, but in a depth limited search we are going into a depth up to a limit which is provided to us. Okay, that is nothing but a alpha. So depth limited search, we can state that it is modification of depth first search if a depth of a tree is very high, it is not advisable to use a DFS. Analyze the problem properly and then fix up some depth up to which we want to search a tree. For example, depth is 3, then we have to, then under that situation the limit assigned is up to the depth limit 3, so we have to carry out a searching process up to depth limit 3. Okay, thus all nodes at level 3 will be considered as a leaf node, and then DFS will go up to a depth limit 3. Okay, so this is regarding to a depth limited search strategy. Okay, so this is video regarding to a depth limited search strategy which is coming under a your uninformed search strategy.